Welcome to the next video in our Ansys simulation software tutorial series where we will be covering finite element analysis, or FEA theory. If you remember in the introduction to the series, I gave you some links to other resources by Dihan Patel and Skill Elite Professional. They understand FEA theory. They have the videos. I do not understand FEA theory on anything more than a high level. I do not have the videos. Think of me as a trained monkey. I can do the thing because someone taught me how to do the thing, and that is about all. So I'm going to link to their videos here so you can access those and watch those videos if you want to understand FEA on a deeper level. But other than that, we're just going to give a high-level overview of what FEA is so that when you're doing FEA through this course, you'll understand what exactly is going on. What exactly is Ansys Mechanical doing when we click the Run button? As we discussed previously, Ansys Incorporated is the company that makes the Ansys software, and this software includes Ansys Mechanical, which is the software that runs FEA. If you didn't pick up on it already, FEA stands for Finite Element Analysis, and Ansys Mechanical runs FEA. It is an FEA program, FEA software. And if you also didn't pick up on it, CFD stands for Computational Fluid Dynamics, which is covered by Matthew, and Ansys Fluent will be running CFD. That is what Ansys Fluent does. Now, I think the name finite element analysis comes from what exactly FEA does. FEA works by breaking down a large and complex geometry like this helicopter, for example, into a bunch of tiny, tiny little shapes, and then you select where to apply a force, like let's say the tail, and you select where to apply a support, like we could support this part of the helicopter. And then it will determine stresses and strains and deformation on the object by applying the force to one element and then systematically solving for each one as it goes through, ending up with a large object that is in a bunch of little cells called elements that is in the shape of the large shape that you originally gave it, but now it's bent a little, or it has this much stress applied to it. And you can use these results for whatever you need. This process can take hours. I've personally left my computer running overnight on some of our rocketry simulations. So depending on the size of the object and how small each element is selected to be, you may be running a very long simulation or a simulation that just takes 30 seconds. HPC, or high power computer compatibility, is built straight into Ansys software. So there's a button you can click under Ansys Workbench that will let you send a job to an HPC if you happen to have one nearby, and that will let you tell the HPC to solve it much faster than you could on your own laptop, and then send it back. If you were running a simulation on the actual entire helicopter with, say, 1 millimeter for each little element, that would take a ridiculous amount of time, and there's no way your computer, your laptop, would be able to run that unless you gave it like 3 days straight to run. So that's why you would be using HPC. Now, unless you're on campus or at the company that has an HPC, you won't be able to use HPC, but it's worth noting. We actually have 2 HPCs at Liberty, I think, and I haven't gotten to use any for rocketry, but I think that they're available if we need to use them, depending on how large our Ansys job is. I'm going to kind of cheat and jump ahead to looking at Ansys just to show you what exactly this looks like. This is the lower airframe of Trinity. So if Trinity was this long, then we've just cut it off about right here, so we can just access the fins to run a simulation on that. So, like I said, FEA works by breaking it down into a ton of tiny pieces. This appears black because of all of the little lines around each piece. If you zoom in, you can see there's a ridiculous number of tiny little shapes through here. Each of them like a ridiculous, like less than a millimeter across. I can actually see, yeah, about a half a millimeter across each one. And if you look under statistics, there are 21,661,000 individual elements in this mesh. And after support was applied here and a force was applied here, we can get the total deformation of the rocket. This wireframe shows where the fin was before, and this is where it is now. And we can get the equivalent stress. So that shows where the maximum amount of stress would be if someone applied forces this way and this way while fixing the top of the rocket. So if you imagine someone standing on these fins like this, or that if the rocket hit the ground coming straight down like this, what would it do to the fins? Well, this is about what it would do to the fins, and that's why we need FEA, so we can find out things like that. And there is actually a nice little animation which Ansys can make to show how it deforms over time. So this is really useful stuff for predicting things when you don't actually want to break the fins of your rocket, or you don't actually want to have to go build the thing. You just want to be able to test it ahead of time. That's why we have computers to run things like FEA for us. And here is that little animation. You can see the fins bending as the force is applied over time with the seconds shown up here. So at this many seconds, this is where it would be. And at this many seconds, this is where it would be. It's really useful stuff. That's all for this brief overview of FEA theory. So, as always, may the Lord bless your engineering. Come visit us at LU sometime, and feel free to watch the next video in the series on Ansys Workbench. FEA works by breaking down really large and complex geometries like this helicopter, for example, or this wooden model of a helicopter, or maybe this Lego working model of the Earth and the Moon going around the sun, or maybe this World War II era's Lego bomber with actual bomb bays, or maybe something like a 1980 something spaceship. Hmm? Or maybe, if you're crazy, the model of the Discovery with the Hubble Space Telescope. Or maybe you're an Avengers fan and you want to simulate the Guardians of the Galaxy spaceship. Or maybe something like this large Lego Technic electric helicopters geometry. Or maybe you're a space nerd and you want to simulate what happens to the Stage 1C of the Saturn V. Or maybe you want to simulate for Stage 2. Or maybe you want to simulate Stage 4B with the lunar lander inside it. You want to know what happened to that? FEA lets you simulate things like that.